Okay, so let's begin today's lecture. Now, first, I would like to discuss the homework assignment I assigned last time. And we know that I assigned 4 problems, but however, I did the first one for you. But still, you need to write the solution by yourself. Just review for it. It will be good. It's a good exercise to review for final, for problem number 1. So I'm going to comment on number 2, number 3, and number 4, right? Okay, well, number two is really simple. So it's tell you that we have 2 functions, f and g, okay? And these 2 functions actually they make a composition function, h equals to f circle g. That's composition function, okay? And then I tell you some information about f and g, along with its derivative at a given point. And so therefore, and you need to find the derivative of the h prime. Okay, so that's the problem. And actually, last time we talked about chain rule. So this solution is just use the chain rule, nothing else. You just plug in everything into the chain rule, you automatically get the result. So here, and g and h, g and f are given, and the h is the g circle f, right? So therefore, h prime 2 is equals to this. So you use the chain rule, so you get this is supposed to be f prime, and composed with g at the 2, then times the derivative of g at the 2. So you plug in all this information there. All this information will tell you it's enough to compute this through this formula. So finally you get minus 15. Okay, so this 3 very straightforward problems. Okay. All right, so let's look at number 3. Number 3, it says that f is defined near A, okay? So this means that f is a function defined in an interval containing A, the point A. And also, it's assumed that f prime at A exists. Now, this is a very important condition. It's a very important condition, okay? And then we want to show that this derivative at A should equals to a new formula, a new limit. So normal limit is fa plus h minus fa divided by h, right? Now this time a new formula is say that the same derivative can be considered as a limit of f a plus h minus f a minus h divided by 2h. So this formula is different from the formula involved in the definition. But however, it tells you that as long as the f prime exists, so this f prime can be computed using this new formula. Okay, but the assumption is that f prime exists. Okay, so this is important, as you can see later, because so even though f prime can be written through this new formula, it doesn't mean that this new formula, new limit, can be accepted as a definition of f prime. Okay, that's a different thing. So this formula works, and as long as the f prime exists. Okay, now if f prime does not exist, then there will be maybe something wrong with it. Okay, all right. So let's see how we can prove it. The proof is very straightforward. Okay, so you can you can rewrite this limit by inserting 2 terms, the minus fa plus fa, okay, in the middle. And then,
did you get to teach anything, or are you just observing?
Excuse me?
Just observing. Today was good though. It was a lot more hands-on.
Yeah.
Yeah.
Any questions?
Middle school, right?
Mm-hmm. They did a. Oh, hold on.
Any questions? All right. So so you can see that the limit by inserting minus a and plus fa, so you can turn this limit into 2 limits, because you can break this down into, so you can roll 1/2 out, So the first one is f a plus h minus fa divided by h. So that looks like the regular limit formula, right? The other one is the limit fa minus h, okay, then divided by h. So it turns out that actually the second one is the same as the first one. There's no difference. Okay, so why? Because the second one is, I mean, the first one clearly is a definition of limit, right? The second limit is also because it's just now, if you think about it, if in the regular definition, you replace the h by minus h, okay, by minus h, then you will get the second formula. Because replace this in minus h, you have a plus a minus h minus fa, right? Then you divide by minus h. But however, if you exchange the sign on both sides, you will see that this is exactly the second limit. So these two limits are just give you the limit. These two limits just give you the derivative. So that's twice the derivative, then divide by 2, you will get exactly fa. Okay, so that's the proof for the number 3. But as I said, you have to be careful on this one. So there's a condition that f prime exists. Okay, if you begin with this formula without assuming f prime exists, you will get something wrong. It may happen that this new formula works for certain function, but however, the function is not differentiable. It's the derivative fail to exist at a. It may happen. Okay, so that's actually is number 4. Number 4 says that give an example to show that the existence of limit in the previous problem does not imply the existence of derivative. So I mean, we have to come up with an example, okay, in which we can calculate the limit. The new limit exists. However, the derivative fail to exist. Okay. Now the example is very simple. You can take the example like fx equal absolute value of x. Okay, choose a equals 0. So the function behave like this. You can see at 0, so you can see this curve, the function fx, the curve carries a corner. Now every time you have a corner, so this means that the derivative will fail to exist, because if you compute the left limit, that's correspond to the left tangent line, slope of left tangent line. It's different from the right limit. That's the right tangent line, right slope of tangent line. They are not equal. So therefore, so at the corner, you can see the derivative fail to exist. But however, if you compute the limit, I mean, the new limit, that limit still exists. Because if you compute the fh minus f minus h divided by 2a, well, here you're choosing a equals 0, so that's why the limit looks like this. And then you can see that f is symmetric. So absolute value of h, okay? The minus h, f minus h is still equal absolute value of h. Then these two absolute value of h cancel. So it's identical equals 0. So therefore limit equals 0. Okay, so this implies that f prime 0 equals 0. And that's a wrong result because the derivative at 0 does not exist. So this new formula is useful only when the derivative exists. Okay, you can express the derivative using this new formula. And so without this assumption, without the existence of derivative, you cannot use that formula. Okay, so that's the main key point of this exercise. All right, so this is exercise number 4. So now today I'm going to continue. So today we'll continue a new section called 5b. It's called mean value theorems. Okay, there's a couple of theorems. And actually in the calculus 1, when you study calculus 1, you may have already know these theorems, okay? But only at that time, you didn't get a chance to know the proof behind this theorem. So today we're going to study the proofs. And all these theorems are very important, okay? Now, so the mean values, there's a couple of mean value theorem. So all these mean value theorem like a sequence, okay? So they begin at a very basic theorem. So the basic theorem is 5.5. It's called interior maximum theorem. So what is mean by interior maximum theorem? Maximum, you may think about maximum value, or you can say there's a corresponding theorem called interior minimum theorem. That's the same nature, the same kind of theorem, okay? So what this theorem says that I have a function f, okay, defined in AB. It doesn't matter the interval is close or not close, okay? Assuming f has a relative maximum or relative minimum at some point C in AB. And then if f is differentiable at that point, then the derivative must equal 0. So that's the interior maximum theorem. It's basically say that as long as you have maximum or minimum, even though they are local maximum, local minimum, then however, the derivative, if it exists at this point, is must equal 0. Now this is a very simple result. I draw a picture for you. So think about this curve. So you can see there's a red dot. So there are 4 points is marked. It's color in red. Okay. So these 4 points are relative maximum, right? On the top I label relative maximum, and there's also 2 points in the bottom. Is actually they are the relative minimum. So relative maximum minimum is means that locally they appear like the maximum value or minimum value, but globally they may not. They may not give the maximum minimum. Okay. So for instance, in this case, and you can see now this maximum minimum or relative maximum, relative minimum will be the global one. Maybe the first minimum point can be considered the global minimum. Okay. The other point, they are not relative maximum or relative minimum. Now, as long as you have relative maximum minimum, then you can see there's a very simple fact you can see. So you can see the tangent line at this point, they're all flat. Okay. The tangent line become flat at the relative maximum minimum. Obviously, it's true. Now, when the tangent line become flat, it's a parallel line to the x-axis. You can see that derivative. The derivative is a slope of tangent line. So at this point, the derivative must equal 0. Okay. So that's the reason why at maximum minimum, the derivative always equals 0. Okay. So here, what we're trying to do is to give a proof. So let's assume that I will take the maximum as an example. I'm not going to repeat the minimum. That's because the same argument. So let's say that f achieve relative maximum at C. So what does it mean is that fx minus fc less or equal to 0, it's become non-negative when x is near the C. Why? Because fc is the local maximum. Okay, dominate the entire value. So fx minus fc cannot become positive, right? It has to be non-negative. So when I say x near C, it can be divided into 2 different situations. X can be near C, but on the left side of C. X can be on the near C, but on the right side of C. Now these 2 things, they will be different. But however, fx minus fc is always non-negative, no matter whether fx is on the left side or the right side, okay? So then you can see that, then you look at the ratio, fx minus fc divided by x minus c. Now think about x is less than c, but near c, less than c. So in this case, the top value is still non-negative, but the bottom value will also be non-negative, or will be positive because x is less than c. Oh, the bottom value will become negative, right? Because x less than c. And then the ratio will become non-negative because top one is non-positive. Sorry, it has to be non-positive. Okay, so the ratio become non-negative. But however, if you let the c on the right side of, let x to be on the right side of c, then the situation changed. Then you can see fx minus fc still be non-positive, but bottom become positive. So therefore, the ratio become non-positive. So when x on the left side, on the right side, the ratio behave differently. The ratio behave differently. On the left side, it's non-negative. On the right side, it's become non-positive. So now let the x approach to c. So you know, based on the definition of the derivative, when x approaches to the c, that all goes to what? Goes to the derivative. Because assuming f is differentiable at c, so this means that derivative exists. So therefore, this limit, two-side limit exists. Or therefore, this limit has to be equal to 0. Because when you approach to c from the left side, the limit turns out it looks like has to be non-negative. But however, if you approach to c on the right side, and the limit has to be non-positive. So therefore, the only way for both limit exist, it has to be exactly equal to 0. Okay, so that's the result. Just hold on 1 second, okay?
Yeah.
Sorry about the, yeah, I have to, something I have to do. Okay, so now you can see that the reason why if you take x goes to c, so this ratio must, the limit of this ratio must equal 0. Okay, so that's why in this situation, this means that the derivative at c equal to 0. Okay. All right, so that's the proof of the theorem 5.5. Now, this is our starting point, okay? And from here, we can begin to prove a number of mean value theorem. Okay. Okay, so the next theorem we want to talk about is called the Rolle's theorem. That's a simplified mean value theorem. Now, statement of this is like this. So suppose you have f continuous. Now, it is very important now that you look at the assumption. F is continuous on the closed interval AB. F is continuous. Any questions? F is continuous on AB. It's closed interval. But however, F is differentiable inside. I mean, in the AB, that's an open interval. So this means that inside AB, the derivative exists. Okay, entire interval A to B, as a closed interval, the function is continuous. So in this assumption, you can see that differentiability is only is assumed at interior point. That's not assumed at the boundary. Okay. Now here the second assumption is suppose at A and B at the endpoint, the F carries the same value. Okay. Then it says that there exists a C in the interior such that FC equals 0. So that's called a Rolle's theorem. Actually, it is very simple. It's actually a consequence of previous theorem. Okay. So if you think about the previous theorem say that as long as you get an interior maximum, interior minimum, then the derivative should equal 0 there. So in this new assumption, we're trying to show that when this happens, then you can always find an interior maximum or interior minimum. And then you can see that at those points, the derivative will naturally equal to 0. Okay. So if you look at the picture, what convince you this is so obvious? If you look at the curve like this, from A to B, you can see the height is the same, the value at A and B the same. Then you can see at this curve, so there must be a maximum there or minimum there. So at this point, at C, so you can see that the derivative should equal 0. But however, we have to still need to prove it using this idea, okay? So first, we can see that since f is continuous on AB, and I know that AB is a compact set. So as from last chapter, we see that as long as you have a continuous function, a compact set, and there are a couple of things you can say, and the function must achieve its maximum or minimum. And the function has to be uniform continuous, and also the function achieves maximum and minimum on this set, right? Now here, we're not talking about uniform continuity. This concept is not going to be used, but we do use the fact that as long as f is continuous on this compact set, the maximum or minimum exists. So by theorem 4.14, so that's the theorem in the last chapter, there exists a C such that f achieves maximum or minimum. Actually, they achieve both. Okay, there are two different points. One point, you can get a maximum, at another point, you get a minimum. Okay, so that funny thing. So here, the point we want to continue to argue is that, of course, you can achieve maximum minimum, but that's not enough, okay? Because who knows? And this maximum or minimum may be just on the boundary, not in the interior. If that happens, then you can see that it's not enough to conclude our conclusion, because our conclusion implies that there is a C, which is inside, it's an interior point. It's inside the single A and B, not on the boundary where the derivative equals 0, okay? So now we know that the function must achieve maximum minimum. The next thing we want to find out is where the maximum minimum can be achieved, can occur inside the interval AB, okay? Now it's come to the condition here. So I know that FA equals FB, right? So we can set FA equal to FB, they are equal to a certain value A, okay? A is a finite value, all right? Now, then we distinguish two cases. Now, unless f is a constant function, that means function is identically equal to A on the entire intervals. And in this case, you can see f prime x equals 0 for every x. Of course, this conclusion will hold, because you can pick any x inside A and B, any C inside, and the derivative should equal 0, right? So that's case one, where f is a constant function. Otherwise, f is not constant function, then you can obviously see that f must achieve maximum or minimum in AB, inside AB, okay? Because the function must carry some value which is greater than A, okay? And that greater value has to be inside A and B, not on the boundary, okay? Then the greatest value, that's the maximum, must occur in the interior, not on the boundary. So that's why you can see that you can find a point inside A and B such that the derivative at this point equals 0. So therefore, this theorem now is proved from the previous theorem. That's the Rolle's theorem. So that's a simple form. It's a simplified form of the mean value theorem. Okay. Any questions? Okay, if no questions, so let's look at the real form of the mean value theorem. Now, this form theorem looks similar. So letting f is continuous on the closed interval AB and differentiable in the open interval A and B, the same kind of condition. But however, it does not assume that FA equals FB, okay? No additional condition. Then it's concluded that there is a C in the interior such that FB minus FC equals to F prime C times B minus A. So that's the mean value theorem. Now this mean value theorem is, sorry, there's a typo. It's not FB minus FC, it's FB minus FA, okay? Equal to F prime C times B minus A. Now this extension of the role theorem, because if we assume FA equal FB, okay, then FB minus FA should equal 0. Then it shows that F prime C times B minus A equals 0. However, B minus A is never equal 0. So we must have FC equal 0. So under the assumption of the role theorem, we can conclude from here that FC equals 0. Okay, now we consider the general case without assumption in the role theorem. Then this is the best I can get. It shows that FB minus FA equals to F prime C times B minus A. Well, we're going to give a proof of this, but however, I want to discuss some geometric meaning of this result. Now, another way to look at this result is like this. So this simply say that the F prime C, if you divide B minus A on both sides. So this formula simply says that there is a C, so that the derivative at the C is equal to FB, equal to this quotient. That's FB minus FA divided by B minus A. So this is another way to express the result of the mean value theorem. Now here I want to explain to you what is the meaning of this quotient. So I can draw a picture here. Okay, look at the first picture here. So that's a situation. You can see FB not equal to FA, okay? And so this curve. Okay, now if you connect two endpoints on this curve, that means from the left endpoint to the right endpoint, and draw a line. So this is a line, it's called, we know it's called a secant line. Secant line connecting these 2 points, right? Now if you compute the ratio, you compute the slope of this secant line. Slope of secant line means the change of y divided by the change of x. Okay, change of y is just equal to FB minus FA. Change of x is B minus A. Take the ratio. So this is exactly equal to the ratio of the right side. So you can see the right side, in the right side, the ratio corresponds to slope of the secant line, of this secant line. So now you can see the result simply say that there must be a C in between A and B, so that the slope of tangent line is the same as the slope of the secant line. So that means this tangent line should be parallel to the secant line. Obviously, you can see this is true, right? It's very easy to understand, okay? And also another thing you have to pay attention is that the existence of C may not be unique. There's more than one C satisfy the same condition. Like in this case, you can see there's a C1 and C2, and both C1 and C2, the derivative equal to this quotient. Okay, so the theorem is just saying that there exists one. It doesn't say that there is a unique one. There are more than one. Okay. All right. So now the proof is kind of non-trivial. In order to prove it, we are going to define a new function called capital Fx. It's equal to fx, little fx, that's our original function, minus a function called fa is a constant, minus x minus a divided by b minus a times fb minus fa. So I define this new function. Now here, I want to again talk to you about what is idea behind this new function. Why we are consider this new function a strange animal. Why we're doing this? Okay. Now, first, you see that this capital Fx is made up by original function Fx. The original function may be a nonlinear function, right? Then subtract a linear function because the extra part consists of constants like Fa, Fb, they're all constant. Then the only place you can have x is x minus a. So it's subtracted by linear function. Now, what is linear function? What is the meaning of this linear function? If you look at this graph again, and you go back to the secant line, and you look at the secant line. So you know that, so we know that 2 points will determine a unique line. Okay, so the secant line is uniquely determined by endpoints. is uniquely determined by the endpoint. So using the analytic geometry, you can write down the equation representing this line. This equation is exactly the equation subtract from the little fx. So this line equation is y equals to fa plus x minus a divided by b minus a times fb minus fa. That's a line equation, basically. So now you can see that I take the original function fx and compare it with the secant line equation, okay, secant line equation, and look at the difference. And then I'm trying to apply the Rolle's theorem on the difference to get the mean value theorem here. Now, why you can do that? Because if I subtract these two equations, you can see at endpoint it carries the same value because you can see the line, the secant line going through the same endpoint. Okay. So this means that we consider this new function. Then you can easily see that this new function is still continuous. Okay, differentiable in A and B because linear function is always continuous differentiable. Okay, also the little f satisfy this condition. Now, very importantly, you'll see that the FA and FB equal 0. Now, this is so obvious from the graph, but it's also obvious from the formula. For instance, if you plug in x by a, look at the right side. X replaced by a, you can see FA minus FA equals 0. All right? Then on the second part, you have a minus a on the top, also equals 0. So the entire second part disappears. So FA must equal to 0. The same thing is FB, because if you plug in x by b, then the first part on the right side is FB minus FA. On the second part, replace x by b, then on the top it's become b minus a. Well, we cancel with b minus a on the bottom. Then you will have a negative sign in front of it. You still have FB minus FA, cancel with the first part. So FB also equals 0. So this means that if you look at this new function, the capital Fx, this new function actually satisfies the condition assumption in the Rolle's theorem. Okay. So here Fa is not just equal to Fb, but they're actually equal to 0. So therefore, by the Rolle's theorem, there must be a C as an interior point for that the capital F prime C as equals 0. So I mean the capital F, its derivative at C is actually equal to 0. Now, so let's compute the derivative of capital F. Because I can do that because at the right side, the capital F is made by the little f, the plus a linear function. We know how to compute the derivative for linear function, okay? So taking the derivative on both sides, you have the first term is f prime x. Okay, then FA is a constant, so taking derivative becomes 0. Now for the second part, you're taking derivative, what do you get? You get 1. Or the top part you get 1. The bottom part remains the same, it's a constant. It's a b minus a. So therefore, after taking the derivative, the second part becomes FB minus FA divided by b minus a. Okay, so it's just a ratio, it's a constant. Okay, so therefore you can see that if I know that capital F prime C equals 0, so this will give you the little prime C, little f, the prime C minus this ratio equals 0. So this means that removing everything to both sides, you times b minus a, you get the result in this theorem. So that's how this theorem is proved. This is a very important theorem. It's called mean value theorem. Any questions? Okay. Now there is a variation of this theorem. It's called the next theorem is called is A5.8. It's called Cauchy mean value theorem. Okay. So this is an extension of the previous theorem. It's more complicated. Now this theorem actually involves two functions, f and g. They're both continuous on a and b as a closed interval and differentiable in a and b as an open interval, okay? So both functions satisfy the same condition we've seen from the previous theorem. And then conclusion is what? The conclusion is say that there must be a C such that, now it's a complicated result. It's called F prime C times GB minus GA equals G prime C times FB minus FA. Now, this result is kind of symmetric. It's a very beautiful result, okay? Now, there's a couple of things I have to mention before I can go into the proof, okay? The proof is non-trivial. Now, first, we'll see that this is an extension of the previous result. Now, here you have two functions, f and g, okay? Let's consider the case where g is just a function x itself, just gx equals x. So this is a special case, right? Gx equals x. Now, if gx equals x, then you can see on the left side of this result, you will become f prime c times b minus a, because gb equals b, ga equals a. On the right side, g prime c, okay? Now, because g is x, so g prime is always equal to 1, no matter what point you choose, always equal to 1. So g prime c equals 1. So then other part is fb minus fa. So if g equal to x, then this result simply says that f prime c times b minus a equals to fb minus fa. This is precisely the result from the previous theorem. So that's why you can see that so this is actually this is actually extension of the previous mean value theorem. That involves two functions. Okay, so that's one thing I want to say first. Another thing is that actually this theorem has an additional connection. Okay, you can see somehow people are trying to derive this Cauchy mean value theorem from the previous theorem by applying the previous theorem directly to f and g. So let's first look at this approach. Okay, now I'll tell you that this approach is not going to work to get this result. But however, you'll get a very close result. But it's deserved to understand this approach. Okay. So the question is, mean value theorem implies the Cauchy mean value theorem, and there is a way to think about this way, to think about it. So the assumption saying that I can apply both mean value theorem to f and g. Okay, so this means that there are two C or C prime in AB, such that f prime C equals to f prime C minus fb minus fa divided by b minus a equals 0. So that's basically the result of the mean value theorem applied to the function f. Now, similarly, you can apply the same result, mean value theorem to the function g, you will get the second equation, okay? But you know that there are maybe two different C, okay? There's no way you can, because the mean value theorem does not specify the location of C, so you cannot tell. The only thing I know that the C is inside A and B, it's between A and B. So you have two different C probably. One is C, the other C prime. And this is the best you can say. Now here, the idea is that you have both results, right? And then I make a connection of these two results. How I can do that? Because if you take the first equation with the function f, okay, you manipulate it. You turn the quotient on the right side, move the quotient to the right side. Then you divide fb minus fa. Okay, so you'll get the 1 over b minus a on the right side. And do the same thing on the second equation for g function. Then you can see this, the right side also equal b minus a. Now, you can see that this approach has a flaw. It's not going to be, so at this time, in general, there's a problem with it because you are dividing fb minus fa, also dividing gb minus ga. But how do you know that the FB minus FA not equal 0. If they are equal 0, you cannot divide. Okay? Now, of course, I know that when FB equal to FA, FC has to be equal 0 by the Rolle's theorem. Okay, but however, then you are facing the question about 0 divided by 0. It's just indefinite. Okay, but anyway, let's forget about these small problems. Let's think about this approach. So you can see, based on this approach, you can see both equations will carry the same term on the right side. So that's the place I can glue these two equations, because one will be A equal to one will be A. So therefore, I can equal the left side together. Equal to the left side together, then you multiply, so you will get this, right? And then you can cross multiply. You cross multiply, then you get a kind of the result predicted by the Cauchy mean value theorem, except that you cannot tell the distinguish C and the C prime. Okay, so this approach tells us that there are 2 points, C and the C prime, and to make them equal. But however, this does not enough. It's not enough to prove the Cauchy mean value theorem. The Cauchy mean value theorem is that it's true that the C actually equal to C prime. So there's only one C there on both sides. Okay, but this approach is interesting, but does not produce the entire Cauchy mean value theorem, but at least it tells you some connection between these two theorems. Okay, so because you can see this approach does not give you the same C, so therefore we must come up with a new approach to prove the Cauchy mean value theorem. Okay, so now let's see how we can prove the Cauchy mean value theorem. So here I'm going to define a new function. So the idea is to forget about the mean value theorem, trying to use directly the Rolle's theorem. So I define a new function. It's complicated. This time, this new function has no geometric meaning. I mean, it's difficult to express this. Okay, so this function is basically equal to FB minus FA as a constant times GX minus GA, and then subtract the same expression with G and F exchanged. Okay, it's called this H function. So this H function will satisfy the same kind of condition. The H is continuous on AB as a closed interval and differentiable in AB as an open interval. Okay, and moreover, surprisingly, you can see that HA equal to HB both equal 0. Because if you plug in, for instance, if you plug in the X by A, okay, so then the first part involves GX minus GA. So once X is replaced by A, the first part becomes 0. Okay, the second part, now because you have Fx minus Fa involved, so if you plug in X by A, you are getting Fa minus Fa is also equal 0. Okay, so that's why HA equals 0. Now if you plug in X by B, if you plug in X by B, then the first part become FB minus FA times GB minus GA. Okay, the second part is GB minus GA times now is FB minus A. That's exactly the same thing, same term with the minus sign. So that's why they canceled. So therefore, HB is also equal 0. Okay. Now, because of this, you can see that it satisfies the Rolle's theorem, the assumption in the Rolle's theorem. So I can apply the Rolle's theorem here. So by Rolle's theorem, there exists a C, unique C. Not necessarily unique, just one C. So H prime C equals 0. Now let's compute the derivative of H. So in order to compute the derivative of H, let's recall what is H. Okay, H is given by here. So you're taking the derivative. So you can see it will be because FB minus FA is a constant. So this constant times G prime X. The derivative applied to GA equals 0. Okay. Then minus GB minus GA times F prime X. And now you plug in H prime C, X by C. You know H prime C equals 0. So that will give you the right side with X replaced by C also equals 0. So this is just the result of the Cauchy mean value theorem. So that's how this theorem is proved. Okay, so that's all I have to say today. And you can see that we talk about 4 theorems, all related to the mean value theorem. They're based on the interior maximum theorem. Okay, then prove one by one, you can get the Cauchy mean value theorem. Okay. Okay, next time we'll continue, and the next time we'll talk the rest of the chapter. And again, so today I'm going to assign 2 homework, the homework number 6 and number 8. Okay, 6 says that suppose f is differentiable on R, and f prime is bounded. Okay, now, so the function is defined on the entire line, and the derivative of f is bounded. Okay, that this means that the f prime x absolute value is smaller than certain given number. Then you prove that f is uniform continuous. Okay, think about it. So this is something connected to the mean value theorem. Okay, the second one is also interesting. So assuming f satisfies the condition fy minus fa, the absolute value is controlled by y minus x squared. Now this is true for all the xy. Okay, then we are going to show that f is a constant. F is a constant. Okay, and so also think about it connecting. This is also connected to the mean value theorem. I will talk about this to homework problem next time, but you need to try this by yourself. Okay. All right, so this is all I have to say today. Any questions? Okay, if no questions, then we can finish here today. Okay, thank you.